So, you saw this video clip where I had a disk which was rotating, and then a small particle or small object, ring type object was placed on that disk. We had x axis, y axis drawn, and then we saw what is the path of the particle with respect to the disk, because the path was traced out on the disk. So, we could very easily see it leisurely. So, this was the disk, and then the disk was rotating, but then we will work from this disk frame. Okay. So, I have an x axis here, I have a y axis here fixed in the disk, and we are talking from the disk frame. For discussing the path of that object, the disk is rotating. When I say that disk is rotating about the z axis, I am using the lap frame. But then when I am saying this is the path of the object, I am using the disk frame. So, that which frame I am using when I am telling some statement or some sentence, that is very, very important. So, from the disk frame, when I am talking in the disk frame, from the disk frame, x axis and y axis do not rotate, they are fixed. They are fixed in this frame, they are fixed. So, I do not have to turn the axis like that. Now, I put the particle here, that small black ring type object, I put it here, and then I gave it a rotation. When I say I gave it a rotation, I am talking from the lap frame. Okay. But the path of the particle is still seen in this disk frame. So, in the disk frame, this was going like this. You saw it, it went like this, and then it reached the periphery. So, if I look from the z axis, which is the axis of rotation of the disk from the lap frame, then the distance from this z axis is increasing. Initially, I had kept this much of distance, but as time passes, the distance becomes larger. So, something is if I am using the language of Newton's second law, though I am not entitled to do that, but I know how to get the license to do that. I will be using proper pseudo forces, and then I can always use the language of inertial frames. So, we are actually looking for those pseudo forces which will allow me to use the language of Newton's first law, second law, third law, and therefore, if I am using that, there is some force which is pushing it away from the z axis. The distance from the z axis is increasing. It is not always to remember that if distance is increasing, then you have a force in the radial direction, you can have radial acceleration 0, but at least in this case it seems that yes. So, you have to use pseudo forces, and then one force seems to be away from the axis, away from the z axis, which is the axis of rotation of this disk frame with respect to the lap. So, this is one, and then it is not only going away from the z axis, it is also turning. So, when it is here, it turns this way, when it is here, it turns this way, when it is here, it turns this way, and the direction of velocity is rotated only when you have a force, component of force perpendicular to the velocity. If you do not have that component, speed will increase or decrease. So, if you have a component which is perpendicular to the velocity, then that component will turn the path, turn the direction of the velocity, and here it is turning. So, there should be a force which is perpendicular to the velocity. So, this is one, and then the other is a pseudo force which is perpendicular to the velocity. At least a component should be there, perpendicular to the velocity. So, in the rotating frame you do have two pseudo forces, or you have to assume two pseudo forces if you want to use Newton's laws. Then together with the real forces you have to use at least these two forces. Now, this one is called centrifugal. It is an example of, it is not definition, it is an example of what we call centrifugal force, and this is an example of what we call Coriolis force. Okay. So, this was some kind of a feel. I tried to give you a feel that in a rotating frame of reference you need two kinds of pseudo forces. Now, let me take one more example. Same story. Let us say, let us use this same figure here. Let us use the same figure. There is a disk and there is an x axis, there is y axis, and in the lap frame the disk is rotating about the z axis. So, it is rotating about the z axis with some angular velocity omega, and we will be using this axis, this y axis, x axis and z axis, which are fixed in the disk frame. To observe the motion of a particle or an object which is placed at rest in the lap frame. Okay. So, suppose I have a particle somewhere here, and this particle or this object is at rest, where do I write? Let me write it here. Okay. This is the particle P at rest. P is at rest in the lap frame. And I am looking at this particle from the disk frame, and the disk frame is rotating with angular velocity omega about the z axis in the lap frame. So, that is the situation. What is the path of the particle? Is the particle at rest? Is the x coordinate, y coordinate, z coordinate, or are constant? So, if this is the particle now and it has some x component, this is x coordinate, and then it has some y coordinate and z coordinate is say 0 at this moment. Now, in the lap frame the disk rotates and the x axis becomes like this. So, the particle has come to on the x axis. Particle was not on the x axis to start with, and now the particle is on the x axis. So, the particle is not at rest, particle is moving. So, that means the particle is coming down, it is from the disk frame. I will say that from the disk frame my frame is not rotating. In the disk frame x axis is fixed, y axis is fixed, and therefore, the particle is here, and then the particle comes here. So, if you work out, it is going in a circle. If in the lap frame, if the disk is rotating this way, this particle is going in a circular path, like this. If it is going in a circular path, it is in acceleration, Okay. So, in the disk frame, if I want to use Newton's second law, there is an acceleration. So, I have to assume some pseudo forces. The real forces is 0, F total, F net. Net means the real force, sum of all real forces, This particle, this object may be placed on a table. So, the gravity, mg, the normal force, everything add to 0, sum of all real forces is 0. But then I have to supply pseudo forces. So that you have this acceleration using Newton's second law. All right. So, the centrifugal force will be there, and what will be that centrifugal force? That will be, that you can obtain from other examples also, and you know it very well, that the centrifugal force, I am using disc frame. So, there is a centrifugal force, and that centrifugal force will be away from the axis, and its value will be m times omega square times m times omega square times distance from the axis. All right, distance from the axis r. What is distance from the axis? Here is the axis, this one, this, let us call it capital X, and let us call this radius as r. This will not be needed. So, centrifugal force will be this m into omega square into that capital X. Which direction? Outward. But the acceleration is inward. This particle is going in a circle, and when the particle goes in a circle, the acceleration is inward. And how much is that acceleration? If it is going in a circle of this radius x, if the particle is going in a circle with this radius x, and the angular velocity of this particle is also omega, the magnitude, because there is the same time period after which in the lap frame the x axis will return at the same place, and the particle will have the same coordinate. So, the angular velocities of the disk in the lab and of the particle in the disk, they are going to be equal. Okay. So, the centrifugal force is this much outward, but the acceleration is, omega square x inward. Okay, in terms of speed it will be omega square x. So, the centrifugal force is outward, but the acceleration is inward. That means I have yet another force, yet another pseudo force, and that is inward, and that is more than this and more than this, and that gives me this acceleration. So, I have Coriolis force, I must have Coriolis force, I must have another pseudo force, and this depends on the velocity, and that should be equal to 2 times m omega square x, and that should be inward. And then this is pseudo force number 1, and this is pseudo force number 2. One is outward, one is inward. Inward is double of the outward. So, this resultant of these two will be inward, and the magnitude will be m omega square x, and then yes, mass times acceleration will be equal to the total force. Total means the real and the pseudo. So, these are some examples where you can work out what this pseudo force is, what the Coriolis force is. Now, but remember, they may look very similar. Apart from the factor 2 and the direction, they look very similar, m omega square x. But this one is like m omega times v, right? Omega into x is v. Okay. So, I would like to write it as 2 m omega v, because it is dependent on the velocity. If the velocity is not there, Coriolis force is not there. If you consider that Bohr's model, you have a plus q charge here and minus q charge here going in a circle with some uniform speed. So, if I put up a frame which is rotating at that same angular velocity as this charge is not moving in that rotating frame. If it is not rotating this frame, then the actual force, real force is you know, E minus q square or q square by 4 pi epsilon naught, and this radius square inward, force of attraction, okay, inward. This much is the force, but this particle is at rest. This particle is not going in a circle. I am talking from that rotating frame. my frame is rotating, and from that frame I am analyzing the motion of this particle, and in that frame, in this particular case, the particle is not moving, it is at rest, and therefore what pseudo force I require? The total force should be 0, the particle is at rest. So in the disk frame or in the rotating frame, I set up a frame which is rotating. I set up a frame, this is x axis, this is y axis, and then this whole thing is rotating in the lab, and when I go to that frame, I find that my particle has same x coordinate, same y coordinate, same z coordinate all the time. It is at rest, and therefore if I want to use Newton's laws, the total force should be 0. But I know that there is an attraction that cannot be done away, and therefore the pseudo force that I have to use, is just q square by 4 pi epsilon naught r square outward, and that is a centrifugal force. That is centrifugal. I do not need Coriolis force. Coriolis force depends on the velocity. If there is no velocity of the particle in my rotating frame, I do not need Coriolis force. So here I will be writing this as, I will not write this as omega times v. Centrifugal force depends on the position, and the Coriolis force depends on the speed, on the velocity, direction and magnitude of the velocity. So this difference one should take care. Let me now derive a formal expression for centrifugal force and Coriolis force if a particle is in motion with respect to the rotating frame. So let us have a rotating frame. So let me draw axis system, some axis system which is rotating in the lab, and the angular velocity is omega. Let us take this z axis as the axis of rotation, okay, and then x axis and y axis are rotating, and in this frame, in this rotating frame, there is a point A or point P which is fixed in this frame. There is a point P which is fixed in this frame, and I am looking at this vector OP. It can be a particle, and this OP can be the position vector of the particle or any vector, this vector OP. I am talking of the vector OP. Point P is fixed in the rotating frame. All right. Therefore, from the rotating frame, so OP is constant, fixed, not changing in the rotating frame. But OP is changing. OP is changing in the lab frame, which is supposed to be inertial in the lab frame. I am interested in at what rate this OP is changing in the lab frame. Okay. So what I do? This particle P, since the entire frame is rotating about z axis and the P point is fixed in that frame, so P is also rotating about the z axis and it is going in a circular path. It is going in a circular path. Okay. So it is going in this circular path with angular velocity omega, and therefore OP is here. After some time OP will be here. I am now talking from the lab frame. I need ddt of OP in the lab frame. After some time the frame will be here, this OP will be here, P point will be here, and so on. So it is rotating. So if I just look for this point P, so let me draw this diagram again. This is the path of that point P, of that particle P. So let us say particle P is here at some instant, and this is the z axis, and this is OP vector, this is OP vector, this is OP vector. Let me call this A, let us name it OP vector, I will call it A vector. So this is A vector at this time. After dt time, what will happen? After dt time, this particle will reach here, and this angle will be omega t. This angle will be omega delta t. After delta t time, the particle will be here. So this was vector A at time t, and this is the vector A at time t plus dt. And this is a change. This is that change. This is that change. This you can say this is delta A, which is A at t plus dt and minus A at t. This is that vector. And divide by time, you will get this ddt of OP in the lap frame. Okay. Now, and this is our origin is here, remember, our origin is here. So this is not actually the A vector, this is the A vector, OP. This is that A vector, and this is that A at time t plus dt. This is it. But nevertheless, things will not change much. Okay, this is your A at t plus dt, and this is A at t. But still this remains this much. So ddt of OP is same as, let me call this point C, the center of this circle. This is ddt of OC and plus Cp. This vector OP can always be written as OC plus Cp, and OC is fixed. OC does not change with time. This particle goes in a circle, and this is the center of the circle, and that will remain always there as time passes. So this is essentially ddt of Cp. Okay. So that's why this original diagram is also valid. Now, how much is this? What do I write for this? This is Cp, this is Cp, and the ddt of is this one. And how much is this? The magnitude? This magnitude will be this length here, Cp, which is fixed, and then into omega into delta t. Okay, so this is the length of this, and the direction of this delta A vector is along the tangent, along the velocity. Okay. So how much is this now? Ddt of that, if you do this delta A by delta t, that is, or it's already written there, that is equal to Cp into omega, this is the magnitude, and along the tangent, and how much is Cp? Cp is this OP, and then if this angle is some theta which is fixed, once again this will be OP times sine theta, and then omega, and the direction is along the tangent. And you work out that this is nothing but cross product of O vector, this omega vector, and this OP vector. See the magnitude. Magnitude of this vector is here. Magnitude of this vector is here. Sine of angle between these two is here. Omega, this is omega vector, and you know what is omega vector? When I am talking omega vector, if the axis of rotation is there, that is the direction of omega vector, and if you are looking from top, then it should go anti-clockwise. So that is the direction of omega vector. So it is omega cross OP, and therefore, what you can write is ddt of vector A in lab is equal to omega cross A, omega cross A. This is an important relation, we will take it from here. Now, this is an important relation, and you can go through this derivation again and convince yourself that the direction of omega cross OP is also along that tangent. How? This omega cross OP, once again you write this OP as OC plus CP, and OC is in the same direction as omega. So, this cross product is 0 and this will be omega cross Cp. Now, it is easy to see the direction. This is a circle, and then you have omega is perpendicular to the circle, and this Cp is radius. So, if you have a circle, this is C here, this is P here, Cp, and omega is perpendicular to the disk coming out. And since it is going this way, so it is going this way, so omega is in the positive direction of omega is coming out of the board. Now, you see what is omega cross Cp. So, this is omega and this is Cp, and omega cross Cp, you can work out what is omega cross Cp. It has to be perpendicular to omega, and therefore, it should be in this plane. It is perpendicular to the Cp, therefore, in this plane it is perpendicular to the Cp. And then you do this omega cross Cp and you see that it is in the direction of velocity. So, you can very easily verify that this whole thing can be written as omega cross OP, and therefore, ddt of this vector A in the lab frame is equal to omega cross A. You do not have to actually differentiate. We will be using this relation very extensively in our rigid body dynamics. You do not have to actually differentiate, you just take the cross product with this angular velocity vector and you get the differentiation itself, provided this A vector is fixed in the rotating frame. This whole derivation is based on that this A vector is fixed in the rotating frame. In the rotating frame it is not changing, then this is true. But if the particle also moves in the rotating frame, this A vector is not a constant vector, this A vector is changing with time even in the rotating frame, then what will happen? You will have to add that term, that is all. ddt of A vector in the lab frame is equal to omega cross A if A is constant in the lap frame, in the rotating frame. If not, the only thing I have to do is I have to add one more term, dA dt is equal to, this is in the lap frame, this is equal to dA dt in the rotating frame, plus omega cross A. So, if A is fixed in the rotating frame, you do not have any dA dt in the rotating frame, then it is just omega cross A. So, because of the frame rotation, you are getting this omega cross A, and because of the particle moving in the, or the vector changing in this rotating frame, you are getting this term. So, this is the relation which is general, more general than this. This is true when A is fixed in the rotating frame, and this is true if this A vector changes in the rotating frame. So, we will start from here.